In this video, we're going to talk about rotational or sometimes angular kinetic energy. Remember that linear kinetic energy we've already learned about is half of the mass times linear velocity squared. Now, mass really for us is a measure of linear inertia. It lets us know how good an object is at not being slowed down or sped up or changed its direction. And v, of course, for us is a linear, or sometimes we use the word tangential speed or velocity. Well, it turns out that this linear kinetic energy, which we sometimes call Klin, is analogous to rotational kinetic energy, which I call Krot. Rotational kinetic energy is half of not the linear inertia, but the rotational inertia, I, and not the linear velocity squared, but instead the angular velocity squared. So this becomes a new equation for us to talk about the kinetic energy that a rotating or a rolling object will have. Let's use this animation to kind of talk about what it is that we just said. As this object rolls to the right, it has a linear kinetic energy that depends on its linear velocity at that center of mass, but it also has a rotational kinetic energy, which depends on its angular velocity, or its omega, as you see it going from left to right. So when we want to talk about all of those things, we're talking about its total kinetic energy. So the total kinetic energy, which I can call k tot, is just the sum of both of those different types of kinetic energy. So we got Klin and then Krot, which really means we have half of the linear mass times the linear velocity squared plus half of the rotational inertia, I, times the angular velocity squared. So that's an equation that we can use to find the total kinetic energy of something that is rolling. Let's use this in an energy conservation problem. Okay, here we have a ball, maybe it's a basketball, that is going to fall to the bottom of this ramp, and it starts at a height of h. If we were going to find the velocity of the ball at the bottom, then what we'd want to do is say this is an energy conservation, so the energy in the beginning equals the energy at the end, and I know the energy that I have at the beginning is gravitational potential, or Yu-Gi-Oh, and at the end I'm going to have kinetic energy, and I know that inside of that kinetic energy I'll be able to find my velocity. Now if the ball were sliding, then we would be able to use just the linear kinetic energy at the end, but because it's actually going to be sliding and rotating, we need to find the Klin and the Krot. Okay, so that means that for this problem, we would say in the beginning you have mgh, then at the end your Klin is just 1/2 mv squared. But now I have this weird term that I don't know what to do with, 1/2 I omega squared. Now for this problem, since it's something like a basketball, we would be using a thin sphere or a hollow sphere, which the moment of inertia for that is 2/3 mr squared, where m is the mass of the ball that I've been using in all of these other terms. So that's good. And r is going to be the radius of that ball. Now, so for this problem, we would plug in that I, so that we get plus 1/2 times 2/3 mr squared. And then we need to do something with this angular velocity omega. Now remember before we talked about how angular velocity times a radius is equal to a linear velocity. Well, it turns out that the linear velocity we need, v, at the center of mass, is going to be the same as the linear velocity at the top. So what we do is we take omega and we plug it in, so that we're going to get v over r squared. Now, before we add the rest of the stuff in, let's simplify this term a little bit. The 2's cancel out. This is going to become v squared over r squared, which I'm just going to go ahead and write that, which means the r squareds cancel out. And what I'm going to get is 1/3 mv squared. And that's really nice because I can combine that with 1/2 mv squared. Oh, and are you really smart? Do you see it? The m's go away as well. So I get gh equals half v squared plus a third v squared, which, you know, if I use like fractions or whatever, I'm going to get 3/6 plus 2/6, or 5/6 v squared. And now if I want to find the velocity, then I'm going to get it by itself by saying that v squared equals, 6 over 5 gh, and then I just take the square root. So depending on what the height is, I now know what the velocity is. And of course, this depends on the planet you're on. For the AP test, you'll use 10 meters per second squared for g. We can also use this method to find the answer to something called the toilet paper drop, which is if you let maybe a yo-yo or a roll of toilet paper or a pulley with something wrapped around it fall from a certain height h down to the ground, and you want to find what the velocity at that point is going to be. Of course, we're assuming that h is from the center of the object, and so you have to adjust accordingly, but it works out pretty well. So for this problem, we would also do an energy analysis. Energy in the beginning equals the energy at the end. And in the beginning, you are not rotating, you're not moving, so you have all potential energy. Then at the end, you're going to have that rotational kinetic energy and that angular kinetic energy. So we'd say 1/2 mv squared plus 1/2 I omega squared, same thing. So let's assume this is a solid disk, and the moment of inertia is 1/2 m r squared, or I guess this is using capital R, so we'll use capital R. It doesn't matter. We used lowercase in the last problem. It doesn't make a difference. So you would plug this in for your rotational kinetic energy term. 1/2 times 1/2 m r squared. And then for omega, you do the same thing. You know that the angular velocity, we use capital R times the radius, equals the linear velocity, or that omega equals v over r. So when you square that, you get v squared over r squared, and the radius disappears in that term. We've got 1/2 mv squared here, and then this term is going to, on the right, that's going to become 1/2 times 1/2, so 1/4 mv squared equals mgh. We can get rid of m. We've got 1/2 and 1/4, so that's going to give us 3/4 v squared gh. And then when we solve for v, we're going to get the square root of 4/3 of g times h. So that's how you find the velocity of the toilet paper roll right before it hits the ground. This is a fun problem, especially if for some reason you decided to watch this video in a particular place. Go you. You're so smart. Congratulations.